Hello everyone. Today I'm going to go over some more homework problems and then we are going to take a look. We're going to start the next section, which is the derivative of some trig functions, some other trig functions. So the first problem I want to take a look at, pages 130, 132, number 9. We're given this function that represents the number of gallons of water that's in a tank. So Q of t is representing the number of gallons of water in a tank. T minutes after the tank has started to drain. So if I go to write this out, Q of t is equal to 200 times 30 minus t, that quantity squared. The questions we need to answer here are: how fast is the water running at the end of 10 minutes? What is the average rate at which the water flows out during the first 10 minutes? So we can't take the derivative of Q of t when it looks like this. We just haven't learned that rule yet. We will, just not yet. So our only other choice is to expand this expression. So I'm going to square the 30 minus t. By all means, if you need to write it out like this, just take your time. So we're going to get a 900. Outside and inside is going to give me a minus 60t and then plus a t squared. So 200 times 900 is actually going to give me 180,000 minus 12,000 t and then plus 200 t squared. So now I'll find q prime of t. Derivative of 180,000 is just going to give me 0. Derivative of my middle term is just going to become a negative 12,000 and then plus a 400t. So we want to pretty much find q prime at 10. So this will just become negative 12,000 plus 400 times 10, which is 4,000. So negative 12,000 plus 4,000 will give me negative 8,000 gallons per minute. So it is okay to leave it this way, but I always like, when it's asking a question like this, we like to answer it the same way. So the water is running out at a rate of 8,000 gallons per minute. Now, because we're using the phrase running out, that's indicating direction. So we don't need the negative here. Now we could answer the average rate at the same time here, or in the same way. So the average rate at which the water is flowing out, we're not using the derivative here. We just want to find the change in the number of gallons over the change in time. So for the first 10 minutes would be just Q of 10 minus Q of 0 over 10 minus 0. And then you could just show these calculations. Q of 10 is actually 80,000. Q of 0 is 180,000. And then we'll just have this over 10. Now this gives us a negative 10,000 gallons per minute. Or again, you can say the average rate at which the water is flowing out is at 10,000 gallons per minute. But if you don't use the phrase flowing out, you have to have the negative sign there. All right, now for question 23, we are looking at a velocity time graph. So the first question, when does the body reverse direction? This is when velocity is equal to 0, but a little bit more than this too, because we actually have 4 places that our velocity is equal to 0, but we're not going to include the endpoint. So another way to look at this, we could say the body reverses direction when the velocity changes sign. So when velocity is equal to 0 and changes signs, so that's going to happen because from 0 to 2 our velocity is positive. Between 2 to 7 our velocity is negative, so our velocity definitely changes signs. And then from 7 to 10 our velocity is positive again. So this is going to happen at t equals 2 and 7 seconds. For part B, when approximately is the body moving at a constant speed? So recall, speed is the absolute value of velocity. So if we're looking here, a constant speed, in this case we really don't need this fact, we can answer it anyway, but the constant velocity is a constant right here. Now if they asked what it was, we could say the absolute value of v is going to become the absolute value of negative 3, so that constant is going to be 3 meters per second in this case. But they were just interested in the time interval, so we could say that that's between 3 and 6. So there's our answer. But this is just indicating what that is. All right, now if you just look at the answers that I have posted as a PDF, graph the body speed for the time between 0 and 10 seconds inclusive. So the graph of the speed function is going to look like the graph of the velocity, except this part right here is going to be reflected. So it's going to show up right up here pretty much. Let me draw it a little better. So it's just going to take any negative value for velocity and reflect that. Let me get that out of the way now. Now the graph for the acceleration, this is where you just want to say all your time intervals, and then acceleration is the derivative of velocity. So we could go from 0 to 1, 1 to 3, 3 to 6, 6 to 8, and then 8 to 10. And then the acceleration would just become the slopes of the tangent lines, or the slopes of the line segments, because we're given the velocity function. So just to write that out, this would be 3, -3, 0, 3, and then from the 8 to 10, we can kind of look like at 3 here, we're going down 3 and over 2, so that would be a -3/2. So then when you go to take a look at this graph here, you would see the little line segments, but we would include an endpoint, closed endpoint at the 0 and the 10. All right, let's go ahead and take a look at number 25. Again, we have another velocity time graph. So for A, it's asking when does a particle move forward, and that's going to be when velocity is positive. Now here, velocity is positive. We don't need the slopes of the tangent lines. This is the graph of velocity. So we're looking at between 0 and 1. So moving forward, we're going to include our 0 because it's positive at t equals 0. And over here between 5 and 7. All right, moving backward when v of t is less than 0. So that's everything between 1 and 5. Notice the 7 through 9, that's equal to 0. So then this would be from 1 to 5. And again, it's proper to put seconds after all of these. Now I mentioned yesterday when we look at something that's speeding up, in terms of a velocity time graph here, speeding up is when velocity is positive and increasing. So up here, our velocity from 0 to 1, it is positive, but it's decreasing. Over here between 5 and 6, it's positive and it's increasing. Or when its velocity is negative and decreasing. So that's what we're looking at from 0 to 1. So I was just focused on the velocity is positive and increasing part first. So that's going to be from 5 to 6. Negative and decreasing actually is going to be from the 1 to 2. All right, so speeding up, where velocity is negative and decreasing, so that is from 1 to 2. Between 3 to 5, we're negative, but we're increasing, so it's also between 5 and 6. All right, and then slowing down. We're looking when our velocity is positive and decreasing, or velocity is negative and increasing. So we have positive and decreasing between 0 and 1. And again, we're going to include the 0 because that's our endpoint there. And then we also have between 3 to 5, we're negative and increasing. So we have this part right here. From 5 to 6, that was in the speeding up part, but then also from 6 to 7, that matches the same scenario from 0 to 1. So we also have from 6 to 7. All right, for B, when is a particle's acceleration positive? We're looking at the slopes of the tangent lines because acceleration is the derivative of the velocity. So we'll say positive. All of our slopes are positive from 3 to 6. And then that's it. Negative, our slopes are negative from 0 down to 2. We're going to include the 0. And then also from 6 to 7. And then 0, where we see the horizontal tangent lines, would be anywhere between 2 and 3, and then from 7 to 9. But we're going to include the 9. All right, for C, I gave a hint to this yesterday. When does a particle move at its greatest speed? So remember, speed is the absolute value of velocity. So if we compare the highest point we reach here, and then we have the lowest point right here, and they look almost equidistant, so we can give a reasonable guess. There's no labels for the y-axis. But the absolute value of v is maximized at t equals 0, and then between 2 and 3. So that's all we're really looking at here. We don't actually have a value. It just says when does a particle reach its greatest speed. So we'll say at t equals 0. They look about the same. And between 2 and 3. When does a particle stand still for more than an instant? So that's when v stays at 0. When our velocity stays, not just constant, but stays at rest at 0. So that's going to be between 7 and 9, but we include the 9. All right, so those were the 3 problems from the textbook. Let's take a look at the AP problems. So on pages 25 and 38, both answers were C. If you want to pause the video to go back and try them again, you can, because I'm going to go over these now. But again, pause the video, see if you could redo this if you missed it, and see if you come up with C. All right, so we're given a position function. Remember I said it's usually s of t, but in this case it's x of t. A particle moves along the x-axis so that its position at time t is given by x of t is equal to t squared minus 6t plus 5. For what value of t is the velocity of the particle 0? Well, v of t is x prime at t, and that equals 2t minus 6. Now all we have to do is set that equal to 0, and then t would equal 3. 38 had a little bit more to it. It says the functions f and g are piecewise linear functions whose graphs are shown above. If h of x is equal to f of x times g of x, then h prime of 3 equals what? Well, if we're looking for h prime of x, and h of x is the product of 2 differentiable functions, we have to use the product rule here. So uv prime becomes f of x times g prime of x. So if I'm going to call this u and this v, u is f of x, v prime just we write as g prime of x, plus v, which is g of x, times u prime, so f prime of x. But now I need to figure out what is h prime at 3. So now I just substitute 3's in for the x's. So I want f of 3 times g prime of 3 plus g of 3 times f prime of 3. Now we read the graphs. Now we have to be careful how we read these. F of 3, f is just a function. So if I go to the graph of f of x, that's the green one here. I want to know what is f of 3. So if I go to the 3, I'm looking at this point here. So f of 3 is going to be a 1. Now g prime of 3 isn't just, it's not the same as g of 3. It's the derivative. It's the slope of the tangent line at x equals 3. So I have to go to the graph of g of x. Now when I go to the 3 here and I find my point, I need the slope of the tangent line. So if we look there, that's just what? That should be a 1. And we'll do the same for the other two. Now, g of 3, I actually go to the graph and I want to find that point. So g of 3 is actually 3. And now f prime of 3, I want to find the slope right here. So I got to do a little bit more work. I know I can come back to the graph right here, so that looks like it's a negative 1/3. So now I'm just getting 1, and 3 times a negative 1/3 is a minus 1, so we get 0. But we had to know how to read the graph in this situation. All right, so today we're going to do a little bit more. We're going to start section 3.5, derivatives of trig functions. Now, we already found 2, if you remember. So recall that the derivative of sine x with respect to x is equal to cosine x, and then the derivative of cosine x with respect to x is negative sine x. We're going to use those two to find the derivative of tangent x with respect to x. So we do not want to have to go to the graph. That's going to be a little bit too complicated. I do not want to use a limit definition here. That's also going to be too complicated. But we can rewrite tangent in terms of sine and cosine, can't we? So then this can become the derivative of sine x over cosine x with respect to x. So now we can use what rule? The quotient rule. So go ahead and do that. Go ahead and use a quotient rule to see what this turns out to be. And we'll focus on simplifying later. Sorry about that. I thought I hit unpause, so I'm not sure where this last left off, but if I repeat anything, I apologize. All right, so we have the derivative of sine x, derivative of cosine x. We are going to rewrite this as sine x over cosine x and use the quotient rule now. So if it's not helping, because again, sorry if I'm repeating, but we do not want to have to graph tangent x and try to find the derivative that way. We do not want to use a limit definition. So we're going to use the quotient rule. All right, so if you already saw this, paused it, and worked this out, that's fine. If not, use the quotient rule, try to find the derivative here. So we're going to start with low d high, so derivative, the quotient rule here, we're going to get low, which is cosine x. The derivative of the high part here is going to become a cosine x. Minus, we're going to have a high, which is sine x. D low is negative sine x, so be careful how you write that. All over low, low, so cosine x squared or cosine square x. But now we could do a little bit more with this. We definitely don't want to have to memorize it this way. So cosine x times cosine x is cosine square x. Negative sine x times negative sine x is positive sine square x, all over cosine square x. Again, we don't want to leave it like this. That's a lot to try to memorize. But if you notice that numerator should look familiar. It's a Pythagorean identity. So we're going to have a 1 over cosine square x. I still don't want to leave it like this. It could become a little simpler. This is the reciprocal of cosine square x, which would become a secant square x. So there is our derivative. So we could say the derivative of tangent x with respect to x is equal to secant square x. And we have a third derivative of a trig function to add to our list. We have derivative of sine x, derivative of cosine x, now derivative of tangent x. All right, so I want you guys to try this. Take the derivative of cosecant x with respect to x. Check on your Inspire when you're done. See if you can rewrite that a different way. Pause the video to do this. All right, so hopefully we were just looking at rewriting this as a reciprocal identity. So this becomes 1 over sine x. And we can use the quotient rule here. So again, if we do low d high, that's just going to become a 0 minus high, and we'll have d low, so cosine x, all over sine square x. So sine x times 0 is gone. It's just 0. So we're going to get a negative cosine x over sine square x. Now what we want to do is try to separate this. So I'm going to write this as a negative cosine x over 1 times a 1 over sine square x. Actually, make this a little bit easier. Let's put them both. So we're going to have cosine x over sine x, and then we'll have 1 over sine x. It'll be a little bit better that way. Now, what is cosine over sine? Should be cotangent. So we're going to have a negative cotangent x, and then here again we have the reciprocal of sine, so that's cosecant x. And it is a little lengthy, but that's as nice as we're going to get this. You could also have it as negative cosecant x cotangent x. I prefer to write it this way because it starts with the cosecant, so it's a little bit easier to remember. So therefore, the derivative of cosecant x with respect to x is negative cosecant x cotangent x. So there's our fourth derivative rule. And again, if you didn't do this already, you could type that in, check on your calculator. All right, before I show you this assignment, I wanted to take a look at that number 16. All right, so just reading a little bit about this, it describes launching a rocket. When a model rocket is launched, the propellant burns for a few seconds, accelerating the rocket upward. After burnout, the rocket coasts upward for a while, then begins to fall. A small explosive charge pops out a parachute shortly after the rocket starts downward. The parachute slows the rocket to keep it from breaking when it lands. This graph shows the velocity data from the flight. Notice the y-axis is labeled as velocity, and then time after launch is the x-axis. So if we kind of track the path that's explained up here in the paragraph, we know this part right here is when it's launched. So the engine is burning right now. What's going to happen at the very top? That's the burnout. So following the rest of this, this is where, it says after burnout, the rocket coasts upwards. So it's still, from this part of the track, it's still coasting upwards for a while, and then begins to fall. So we're coasting upward, but the engine's no longer running, so we could say, but it's slowing down. And does that make sense? Because the velocity is positive right here, but it's decreasing. So that's how I know it's slowing down. Now right here at the x-axis, what does this mean? Our velocity changes signs here, so it's 0, but then it changes signs. So this is when our object, this is the max height that it reaches, because then it's going to start to change direction. Max height is reached, but it changes direction. So when it changes direction, it starts to fall. Now this velocity is negative and decreasing. It starts to fall. It's still, so yeah, we'll just say this. So it's falling right now. And then what's going to happen right here? That's where the parachute opens. And then this last part of the trip, it's still falling, but not as fast. All right, so the questions we're looking at here. For question A, how fast was the rocket climbing when the engine stopped? So if we go to our graph, it looks like right here, almost to 200, so at 190 feet per second. We're just looking at the y value, the velocity value at that time. For how many seconds did the engine burn? We're just looking at the x-axis here, so it looks just like for the first 2 seconds. C, when did the rocket reach its highest point? So we analyze the graph right here, a little over, we'll say maybe 9. My graph shifted a little bit here. Hang on one second. There we go. I just had to realign it. Now that looks better. That matches the 8. All right, so it says, when did the rocket reach its highest point? What was its velocity then? So the velocity definitely 0, and it reached it at 8 seconds. D, when did the parachute pop out? So we have that here. So we have that here. Looks like right about 11 seconds. How fast was the rocket falling then? And again, we're just looking at speed, so it looks like a negative 90, but that's just because the negative indicates it's the direction. So again, we're really answering speed at this case, so 90 feet per second. E, how long did the rocket fall before the parachute opened? So it started falling at 8 seconds, parachute opened about 11 seconds, so that's going to give us 3 seconds. And then F, when was the rocket's acceleration the greatest? When was the acceleration constant? So the acceleration is the greatest. We're really looking at the slopes of the tangent lines here. So acceleration is the greatest. We're looking for the steepest slope, positive slope of our tangent line. And that looks like it's happening right up here. So if we had to draw in tangent lines, we're getting the steepest right about here, like right before 2 seconds there. And the acceleration is constant between 2 and 11 seconds because all the slopes of the tangent lines are the same if we were to draw them along this line that's right here. All right, so I really like this problem. It forces you to analyze a graph, a velocity time graph. It forces you to look at the relationships between velocity, position, and acceleration as well. All right, here were the other problems, 18 and 22, that I assigned. I'll go over these tomorrow. And then here's your assignment on page 133, try number 31. Still, if you need to, go back over the problems I just went over with you. Derive the derivative of cotangent x and secant x. And then here are some more AP practice problems. Now on page 65, number 76, you can use a graphing calculator. And on page 82, number 6, you can use a graphing calculator. All the others, no graphing calculator. Take care, guys, and let me know if you have any questions.